It is 6:47 in the morning, somewhere outside Lyon, France, and the ground is moving, not shaking, not trembling from an earthquake or a passing truck. Moving, as in the soil beneath the ballast bed, is compressing and releasing in a wave that travels at nearly 186 miles per hour, chasing a machine that is already half a mile ahead of it. The TGV Sud-Est, train à grande vitesse, high-speed train, has just cleared a curve section at 168 miles per hour. On board, 345 passengers are reading newspapers, drinking coffee, staring out windows at farmland, blurring into a single horizontal smear of green and brown. The ride is smooth, quieter than expected. Nothing feels wrong. Outside, 10 feet below the carriage floor, the rail surface is absorbing 17 metric tons of dynamic load per axle per second of travel. The pantograph above the roof crackles against the overhead wire at 25,000 volts. Air pressure around the nose of the train has been compressed into a wave. Not a metaphor, not a loose analogy. An actual pressure wave. A column of displaced atmosphere being pushed forward at train speed, rebuilding behind the tail. And somewhere ahead, a northbound service is running. 2 trains, same track corridor, opposite directions. When they meet, the pressure differential between them will be measured in kilopascals. The passengers will feel it as a pop, an ear-clearing, jaw-tightening pop, lasting roughly 0.4 of a second. On some early runs, before the engineers understood the full aerodynamic signature of these machines, that pop wasn't a pop. It was an implosion. Glass buckled inward, seals failed, structural window frames bent. This is not a story about a disaster. No one died from a shattered window on a French high-speed train, but the windows shattered, and understanding why, and what had to change to stop it, tells you something essential about the physics of speed, and the gap between building a machine that can move fast and building a world that can survive it. Speed has always been an engineering problem, but high speed, the kind that crosses 150 miles per hour in revenue service, is a different category of problem entirely. Below roughly 100 miles per hour, a train's aerodynamic profile is a secondary concern. Engineers focus on rolling resistance, track geometry, suspension dynamics. The air is a nuisance, a drag coefficient to be minimized. Above 150 miles per hour, the air becomes the primary engineering constraint. At those speeds, a train is not moving through air, it is colliding with it, continuously. At highway speed, the pressure differential between the front and rear of a locomotive might be measured in tens of pascals, barely enough to notice. At 186 miles per hour, that same differential climbs to hundreds of pascals. At 220 miles per hour, it crosses into territory that structural engineers must account for the same way they account for static load. The nose of a high-speed train set is not shaped the way it is because of aesthetics. The long, tapered, often asymmetrical profile of a TGV, a Shinkansen, an ICE. Those shapes are pressure management devices. They exist to ease the displaced air column to the side, rather than pack it into a compressing wall ahead of the train. The Japanese learned this first. The Shinkansen entered service in October 1964, connecting Tokyo and Osaka at speeds that no passenger rail system had ever attempted in revenue operation. Engineers had designed the track. They had designed the rolling stock. They had calculated the traction requirements, the braking distances, the clearance tolerances. They had not fully calculated what happened when a 16-car train set entered a tunnel at 130 miles per hour. The tunnel compression event was almost immediate. When a high-speed train enters a tunnel mouth, it does not slip into the bore. It plugs it. The cross-sectional area of the train occupies a significant fraction of the tunnel's internal diameter, and the air ahead of it has nowhere to go except forward. Compressed, accelerating, bouncing off the tunnel walls and the nose of the train simultaneously. The pressure wave races ahead through the tunnel bore. It exits the far end, not as a quiet dissipation, but as a boom. A sonic pulse felt by residents hundreds of meters from the tunnel portal. Cups rattled on tables. Dogs reacted. People filed noise complaints before they had language to describe what they were hearing. Inside the tunnel, the wave is worse. Passengers experienced abrupt pressure changes. Ears popped, then popped again as the reflected wave returned from the far end. Window seals, designed for standard rail service, were being subjected to cyclic loading they had never been tested against. Some failed, not catastrophically, not dangerously, but glass cracked, seals delaminated, structural frames bent micrometrically out of tolerance. The engineers went back to work. The solution to tunnel compression was not one solution. It was a system of solutions he applied simultaneously over decades. The first intervention was geometric. Tunnel portals, the entry and exit mouths, were widened and given flared profiles. Instead of the train entering a hard-edged rectangular bore, it entered a gradually constricting throat that allowed some of the pressure to escape laterally before full compression occurred. The physics were similar to a Venturi effect in reverse. Give the displaced air a path to move, and it will not build into a wall. The second intervention was structural. Train windows on high-speed rolling stock began to be designed to a different loading standard entirely, not the static wind load of a train moving through open air, not even the pressure of a passing freight train on an adjacent track. The new standard was tunnel pressure cycling, a dynamic, repeating, a bidirectional load that most window systems had never been asked to survive. Double-pane laminated glass, flush-mounted frames, bonded rubber seals rated for positive and negative pressure simultaneously. Systems that could absorb a 3 kilopascal differential without any internal force reaching the passenger compartment. The third intervention was operational. Trains were slowed in tunnel approach zones, not dramatically, not to the point of defeating the purpose of high-speed rail, but enough to reduce the leading pressure wave to tolerable levels. As infrastructure improved and rolling stock became more aerodynamically refined, those speed restrictions were lifted, incrementally, validated by measurement. That is how engineering works. You don't solve a problem once, you solve it at this speed. Then you solve it again at a higher speed. Then you build the infrastructure to match the machine. Then the machine goes faster again. The open-air passing event, two trains crossing each other in opposite directions, presented a different problem. Not compression, but differential. When two trains meet on adjacent tracks at a combined closing speed of 350 miles per hour, the interaction lasts roughly 1 second. In that second, the leading pressure wave of the oncoming train hits the side of your train with a force that spikes sharply, drops sharply, and reverses. The spike is positive pressure, air being pushed toward you. The drop is the low-pressure wake behind the oncoming train's nose. The reversal is the full aerodynamic wake, pulling at your train's skin with negative pressure as the tail passes. For a conventional rail window, sealed with compressible foam, retained with a rubber gasket, this cycle is fatal. The positive spike pushes the glass inward. The negative pull yanks it outward. If the frequency and amplitude are high enough, and if the window system has any weak points in its sealing or bonding, the glass can lose its retention entirely. Early TGV testing recorded exactly this. Window panels on test cars deformed measurably during high-speed crossing events. Glass did not always shatter outward. Sometimes it buckled inward. Sometimes the seal failed, and the glass simply fell, still intact, out of its frame. No passengers were seated in the test cars, but the engineering teams understood what this meant for revenue service. The problem was not rare. Every time two trains passed on the line, the event occurred. Thousands of times a day, across the full network. The passing event standards that emerged from this testing became foundational to European and Japanese high-speed rail specifications. Window systems were redesigned to withstand cyclic passing loads as a primary design criterion. Track spacing between opposing lines was increased from standard clearance to aerodynamic clearance. Wider, because the distance between trains directly affects the peak pressure differential. Sound barriers along high-speed corridors, often described as noise mitigation infrastructure, serve a dual purpose. They also disrupt the lateral pressure wave, scattering it before it can build full amplitude against a passing train's flanks. The infrastructure and the machine evolved together. Neither could reach its operating speed without the other. America's relationship with this class of problem is complicated because America's relationship with high-speed rail is complicated. The Acela, Amtrak's flagship corridor service between Washington and Boston, reaches 150 miles per hour on short segments of the Northeast Corridor. For most of its run, it operates at 110 to 135 miles per hour, constrained not by the locomotive's capability, but by the track geometry, the signal systems, and the grade crossings that share right-of-way with freight traffic. At those speeds, aerodynamic pressure is real but manageable with existing rolling stock standards. The Acela's Bombardier-designed cars were built to European high-speed specifications, including the window loading criteria developed through decades of TGV and ICE operational experience. But the Northeast Corridor is also full of tunnels, old tunnels, pre-war tunnels in some cases, some with internal clearances designed around steam-era equipment, without the flared portals and geometric refinements that European infrastructure received during high-speed rail construction campaigns. When the Acela enters Baltimore's Howard Street Tunnel, or any of the older bore sections along the corridor, the pressure dynamics are measurably different from modern high-speed tunnel design. The clearances are tighter, the portals are harder edged, the compression event is more abrupt. At 135 miles per hour, current systems handle it. At 200 miles per hour, the speed that serious Northeast Corridor upgrade proposals target, the tunnel infrastructure would require significant modification before the physics becomes safe again. Yet this is not a political statement. It is an engineering constraint, the same one the Japanese faced in 1964, the same one the French faced in the late 1970s, and early 1980s, the same one the Germans faced with the ICE rollout. Every nation that has built genuine high-speed rail has paid this price, has done the tunnel analysis, the window redesign, the track spacing calculations, has built the infrastructure to match the machine. The physics do not negotiate. They simply wait for the engineering to catch up. Today, a TGV duplex leaving Paris Gare de Lyon reaches its operational track speed of 200 miles per hour within the first 12 minutes of departure. The windows are flush with the carriage skin. The seals are bonded, rated, and tested. The tunnel portals along the line are shaped to dissipate pressure longitudinally before it can spike. When two trains pass each other at speed, passengers feel nothing. A slight pressure shift, a change in ambient sound. Gone in a second. The engineering that produces that nothing, that unremarkable, forgettable, entirely imperceptible crossing event, represents 60 years of iterative problem-solving, structural testing, material science, infrastructure redesign, operational data accumulated across billions of passenger kilometers. The absence of a shattered window is not an accident. It is the product. Every kilometer of track that moves passengers at 200 miles per hour without incident is the outcome of engineers who understood that speed creates force, and force requires management. And management requires infrastructure built specifically for the machine you intend to run. The windows don't shatter anymore, not because the pressure went away, because the system was built to absorb it. Under this video, there's a subscribe button. It's a small action, but it keeps stories like this moving. If you're drawn to the systems that operate quietly beneath America's infrastructure, the engineering decisions that make ordinary journeys possible, subscribing simply means you want to see more of what holds the machine together. That's enough.